A very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be talking about a new topic that is called tensor calculus. So let us get started. So the topics for today are, first we'll start with partial derivatives of vectors. Then we'll discuss some notations which are required for discussing tensor calculus. And then we will start discussing tensor calculus through known territory, that is by discussing vector calculus first. In the next lecture, we'll talk more about calculus of tensorial objects and some integral theorems. So first, we will have to define the idea of tensor field. We have talked about it in the past, but we'll discuss it again because we'll be requiring to use this idea in today's lecture. So let us say C is an nth order tensor, which is a function of spatial coordinates x, vector, and t. I'm writing it in a mixed notation that C is written in indicial notation and X is written in the vector notation, but that is because I do not want to use any indices for the vector here for now. But I am sure the idea is clear that the quantity C, which is an nth order tensor, is a function of space and time. We'll also assume it to be continuous and smooth so that we can take its derivatives and so on. So what I mean by smooth is that I can take the desired number of derivatives of the function as required. So we could have a scalar field that we are dealing with for doing tensor operations on it. We could have a vector field, or we could have a second order tensor field like this. So in today's or this week's discussion, mostly we'll be talking about tensors of orders up to 2, but the relations we develop will be general and are applicable to tensors of higher orders as well. Right, so now that we have defined the idea of a tensor field that we'll be dealing with while discussing tensor calculus, now we need to talk about partial derivatives. So let us discuss that. So let's say C is the tensorial object we're talking about. Now for discussion, I'll remove the indices, but remember that C is an nth order tensor for this discussion. So I can write del C by del T, which means that I keep x1, x2 and x3, that is the spatial dependence, kept fixed, and we only see the change in the quantity C as we change T infinitesimally. So that's the partial derivative of a quantity C with respect to time. Similarly, I can also write del C by del x1. So that would mean the change in quantity C with respect to x1, given the fact that the other independent coordinates x2 and x3 and time are kept fixed. And we could have del C by del x2 and similarly del C by del x3. So these are partial derivatives of a quantity C, and these are the only partial derivatives possible because C is a function of these independent coordinates, time, x1, x2 and x3. Now more generally, if I was talking about the partial derivative of C with respect to some spatial coordinate, I could write del C by del xi. So that what that means is that I could substitute any value for I and that would give me the partial derivative of C with respect to that spatial coordinate. So I can use an index here and that would be allowed, and this would be a general representation of a spatial partial derivative of the variable C. So now let us talk a bit about some notation. So just to abbreviate this notation, we also sometimes would write del C by del x1 as partial with a 1 here and C. So this partial with a subscript 1 basically means that this is del by del x1 of C. So this del by del xi, for example, the operator is written as del with the subscript I operator. It's an operator because it needs to have something to operate on. By itself, it is not a quantity as such. So this notation is called the abbreviated notation. Where we write del by del xi as partial I operator. If you have higher order derivatives, let's say del 2 pi by del x1 squared. So that's the second partial derivative of the quantity phi with respect to x1. So this would be written as del 2 with a 1 1 times phi. So del 2 means it's a second order derivative, and since the derivative could also be mixed, so we are clarifying that the first is with respect to 1 and the second is also with respect to 1. Now what if the derivative was mixed? Let us say this was del 2 phi by del x1 del x2. In that case, we'll write it as del 2 1 2 of phi. So this is the abbreviated notation. There's another notation that we'll be using that's called the comma notation. So in this comma notation, this quantity, let's say del phi by del x1, will be written as phi with a comma 1. So that's even simpler than the abbreviated notation. So this is the same as writing del 1 of phi. So these are just notations. You just have to understand how to use them. And when you keep using them, then you don't have to think of the original derivative that you're talking about. It will automatically start meaning the derivative as you use this notation. So we will be preferring this comma notation in this course. So this is preferred in this course. So the reason is it is compact and it allows us to perform the calculus on tensors quite comfortably and efficiently. So let's practice this notation a bit more. So let us say we have a quantity del Vi by del Xj. Now don't worry about what this quantity is and so on. First, let us just worry about how to represent this in the comma notation. So this would be written as Vi, that is a quantity whose derivative is being taken, and we'll say comma with a j. So comma with the j basically would mean this is del by del xj of this quantity. Now we can remove the brackets. So this becomes Vi comma j, which would be the same as in the abbreviated notation if you were writing it del with a j subscript followed by a Vi. Let's try to go the other way around. So let's say if we had the expression sigma I j comma k given to us, what this would mean is that this is the del by del x k derivative of the quantity sigma I j. Let us look at another example. So in this case, we have a mixed derivative, that is del 2 uk upon del xi del xj. How would we write this in the comma notation that we are discussing? So the quantity being differentiated is uk, so that comes here first. Then we use the comma notation, so the uk comma, and then we'll have two indices I and j. So the use of two indices basically means that we are differentiating the quantity twice. In this case, first with del x I and then with del x j. So these are some of the notational techniques to use the comma notation. So let us ask ourselves a question. That is the quantity we just talked about, uk comma ij, the same as uk comma ji? And the answer is yes, but under certain conditions. If both of these are in C2, that is, the second derivatives we find for UK are continuous. So if you were to write this in the traditional notation, this would be del 2 UK upon del xi del xj, and the right hand side would be written as del 2 UK upon del xj del xi. The next question I have for you is, what is the order of the quantity u k comma I j? Now see, this quantity by itself is a tensor. We'll discuss more about it in the next lecture, but for now the question is only about the order. And you know that simply the order is the number of free indices in the term. So in this case, we have 3 free indices, both I, j and k are free. So the order of this is 3. So let's try one more question. What is the order of ui comma ij? So in this case, we only have one free index, that is j. So the order becomes 1 because we have only one free index. Another question or an exercise is, what exactly is phi comma I j? So as I said that we'll be using this comma notation, so one should be able to understand what exactly is this thing. Well, this expands to del 2 phi because you have two indices after the comma, so that means it's a second order derivative upon del xi del xj. So this is the second order derivative of the scalar phi. And what is the order of this? Well, the order is 2 because you have two free indices. So this is a second order tensor. So now that we're talking about order, let's talk about the quantity ui comma j. So what is the order of this? This has an order of 2 because we have two free indices here. And let us see exactly what this quantity is, because ui is a vector, we know that. And what we have done is we have written del ui upon del xj. So notation wise we are comfortable now, but what is the meaning of this quantity? Let's have a look. So we know it's a second order tensor. So let's write sigma ij as ui comma j. We can do that. So if I was to write this in the matrix form, just as we do typically for tensors of second order, this would be written as these 9 terms. And if you're not comfortable still to see what these terms are, I'll also write them in the traditional notation. So this is the quantity ui comma j. In fact, this matrix is an important matrix. So we see that quite often, not just in continuum mechanics, but in other fields of mathematics, particularly in geometry. And we, with our misuse notation, will simply be writing this as ui comma j. So if you remember the misuse notation, then we do not put square brackets. So this could mean a component with certain particular values of I and j, but in the misuse notation, ui comma j by itself is the complete tensor of second order, containing the 9 components. Again, based on the context, you'll figure out what it exactly means. Another question, and remember, through these questions, we are basically figuring out the understanding of this notation in tensor calculus. So what is the order of ui comma I? Well, answering the question is simple because in this case you have no free index. So the order is 0, it is a scalar quantity. So let's move on. Now if I write the quantity del x1 by del x2, what exactly would that mean? So as you can see that x is a vector here, and x actually is the position vector. We've been writing the position vector x like this. So that position vector has 3 components, x1, x2 and x3. I can also write this as xi, ei. So x1, x2 and x3 are the 3 components of the position vector, and position vector is simply a vector that joins the origin to the point P whose position can be represented using this position vector. So it is usually general in nature in the sense that it denotes the general point P where x1, x2, x3 are variables. So this is our 3D Cartesian coordinate system. Then we typically would write a point P having 3 coordinates x1, x2, x3, and the position vector in this case is this vector that joins from the origin to the point P. So coming back to the question, what exactly is this quantity del x1 by del x2? So given that we understand what the x vector is, del x1 by del x2 is 0 because they are 2 independent directions. The answer is this is 0. And if I was to ask you what is del x1 by del x1, that will be a 1, which is the same as del x2 by del x2 and the same as del x3 by del x3. So with this logic, I ask you to think about what exactly is the quantity del xi by del xj. Well, you can guess it now that this actually is equal to the Kronecker delta delta ij. And in the common notation, we can write this as xi comma j, which is equal to delta ij. So now that we know what xi comma j is, what exactly would be if I write xi comma I? Well, since xi comma j was delta ij, so xi comma I becomes delta ii. Right? The reason that xi comma j was just shown to be delta ij. And what is delta ii? Well, that's easy to figure out because this is 3 from the expansion using the summation convention. This becomes delta 1 1 plus delta 2 2 plus delta 3 3, which is a 3. But if I want to see from the left hand side, I can see that easily because this becomes x1 comma 1 plus x2 comma 2 plus x3 comma 3. And x1 comma 1 is del x1 by del x1, so that's a 1. Similarly, x2 comma 2 is a 1, we just discussed that, and x3 comma 3 is 1, so which becomes a 3. So we can see this from both directions that xi comma I is delta ii, which is a 3. Again, this is something we will come across very often in this course, so it's worth discussing that here. So although I discussed this as a question, and I've been doing that for most of the cases today, but remember that these are very much a part of our understanding in continuum mechanics. All right, so now that we are comfortable and confident with the notation in tensor calculus, particularly the comma notation, we will talk about vector calculus, because vector calculus is something we already understand from our undergraduate studies. So we'll apply the tensor calculus rules to these specific cases of vector calculus. And then once we understand doing vector calculus using this indicial comma notation, we will then move to tensors of higher order in the next lecture. So a good starting point for vector calculus is defining the grad or the del operator. So this is the grad or the del operator. In fact, it's also known as the nabla symbol. So this operator is an operator, but it's a vector operator. It's a vector operator. So what it means is that the result of this operator is a vector. So this can be expanded as del by del x1 e1. Remember, if you have something in the bracket here, that something goes in the bracket here, plus del by del x2 e2 plus del by del x3 e3. So if you are applying this grad to a quantity like a scalar phi, this would become del phi by del x1 e1 plus del phi by del x2 e2 plus del phi by del x3 e3. And we know that we can write this as del phi by del xi ei from the summation convention. And this can also be written as, in our comma notation that we discussed today, phi comma I ei. So we can see that grad of phi is a vector with these three components, phi comma 1, phi comma 2 and phi comma 3. And with the misuse notation, we can simply write this as phi comma I. We'll get rid of the ei, and this by itself will denote the vector phi comma I. So I can write grad of phi as phi comma I. Right, so whenever you see this quantity phi comma I, that basically means it's the grad of phi. With time and usage, you'll get comfortable with it. Again, this is something that we must remember, but through solving lots of problems, it will be straightforward for us. So this was the first operator we talked about in vector calculus. Now let us talk about divergence. So we write the divergence of a vector v as the grad operator dotted with a vector v. So this is called the divergence of v, or sometimes written as div of v. By the way, grad sometimes is written as grad of phi. So let us see what this divergence means. So divergence is like a dot product between two vectors. So we write the first vector dotted with the second vector. So let's do that. Although the first vector is an operator, but still it is a vector operator. So we'll write this as del by del x1 e1 plus del by del x2 e2 plus del by del x3 e3 dotted with the vector v. So v is written as v1 e1 plus v2 e2 plus v3 e3. So if I expand this, this will simply become the first component of the first vector times the first component of the second vector plus second component of the first vector times the second component of the second vector and del v3 by del x3. Using the summation convention, this can be written as del vi by del xi, and using the comma notation, this becomes vi comma I. So divergence of v, that is del dot v, is vi comma I. Let us now move to the third operator. Del cross v, which is also known as the curl of the vector v, because it denotes some sort of a rotation, as we'll discuss later in the course. But for now, let's focus on the mathematics here. So to see the cross product, let's recall that the cross product between vectors u and v were written as epsilon ijk ui vj times ek. And in the misuse notation, we simply get rid of this ek, and this is how we write the vector as a result of u cross v. You can see that the index k is free, so it's a vector because it has one free index. So with this understanding, let's write the curl of v, that is del cross v. So this is epsilon ijk, the first vector, which is basically del by del xi, times the second vector, which is vj. In the comma notation, this becomes epsilon ijk vj comma I. So the curl of v in the initial notation becomes epsilon ijk vj comma I. So remember, the index I is coming from the grad operator here, and the index j is coming from this v. That is the reason I comes after j in the common notation, but it is del by del xi of vj. There's sometimes a confusion about the ordering of the indices, but if you go to the meaning of what exactly is curl, this will be clear. Now the fourth operator we'll talk about is called the Laplacian, which is del square of some scalar phi. Let's write this as Laplacian operator. And Laplacian actually is defined as the divergence of the grad of phi. So with this definition, this grad of phi basically results in a vector. So this is like a divergence of a vector. And you know, divergence of a vector was, if the vector was ui, this divergence was ui comma I. So we'll find what this grad of phi is and simply do a comma followed by the same index. So let's do that. So grad of phi is phi comma I, and when you do a divergence of that, that becomes the vector comma I. So if I was to write this, this becomes phi comma I, which is nothing but, if you were to write the traditional notation, this is del 2 phi upon del xi del xi. And if you expand this, this becomes del 2 phi by del x1 squared plus del 2 phi by del x2 squared plus del 2 phi by del x3 squared. And you can check that by writing phi as, grad of phi as del by del x1 of phi e1 and so on. So I'll summarize that the Laplacian of phi is written as phi comma I. So let me now take you through the boxed expressions, because we have written the four most common vector operators in calculus, vector calculus, in indicial notation now. So the grad of phi is phi comma I. The divergence of a vector v is vi comma I. Again, it could be vj comma j. They're all dummy indices. The curl of a vector v is epsilon ijk v j comma I, and the Laplacian of a vector phi is simply phi comma I. Now we have done operations to vectors or scalars today while discussing vector calculus, because as I said, we wanted to be in a known territory, but in the next lecture we'll talk about these operations being applied to tensors of orders second or above. So before we close this lecture today, let us try a problem. So we have to show that the divergence of the curl of a vector v is 0 for any vector v. So let's write this in the symbolic notation. Divergence of the curl of any vector v is 0. This equation is seen in electromagnetism and in fluid mechanics. In fluid mechanics, we see that when we write the curl of velocity as the vorticity and the divergence of vorticity is 0. But again, today we are not worried about that. All we care about is to show this using the indicial notation. So let's begin. First, we'll write the indicial notation expression for the curl of velocity. We just showed that this is epsilon ijk. Then the index I is for the del by del xi. So we have a vj comma I. Then if I write the divergence of this quantity, now we can see that the expression epsilon ijk vj comma I is a vector with the free index k. So if I was to do a divergence of this would become epsilon ijk vj comma I, this whole thing comma k. Because if this whole thing was written as a vector uk, then the divergence would be uk comma k. So let's expand this. Epsilon is simply a number, because it can either be a 1 or a -1 or a 0. So it's a constant for the purposes of taking a derivative. So it can be taken out, and this becomes v j comma I k. So you're taking a derivative of already a derivative. So this becomes the second order derivative that we see here. And the question is, how do we simplify this? Well, we can see that epsilon is skew symmetric in the indices I and k, whereas this expression vj comma ik is symmetric in the indices I and k, because we showed that vj comma ik is the same as vj comma ki if they are smooth enough. We'll assume that, and this is a multiplication now of a skew symmetric tensor and a symmetric tensor, which has already been shown to be a 0 in the past. So this completes the solution. So as a summary, in today's lecture, we started with the understanding of tensor fields. Then we talked about taking partial derivatives of tensors. We talked about notations, particularly the comma notation, because that is something we'll be using in this course. And then we talked about vector calculus operations, such as the grad, divergence, curl, and the Laplacian operators. So with this understanding, we now are ready to move on to applying these operations to tensors of higher orders and discussing the integral theorems, which will help us solving problems in continuum mechanics. Thank you, and let us talk about a concept problem now. So the concept check problem for today says that we have to write the three components of the vector, which is sigma ij comma I. I'm sure you appreciate the fact that sigma ij comma I is actually a vector because it has one free index. So you're supposed to write the three components of this vector. So thank you, and I will see you in the next lecture.